Right, I have some questions about viscous flows, boundary layers, some key definitions as well, and some notations. I'm just going to run through a few things. So chapter 3 of this module dealt with inviscid flows. That means that we assume there's no viscosity, there's no stickiness between the particles. We can define a classification of flow just through Reynolds number. We did this way back in lab class 1. This is a slightly different form. We don't usually see this with this module, but this is the kinematic viscosity. So it's the dynamic viscosity divided by the density. This is inertial force, and this is the viscous forces. So it's a ratio. It's dimensions number. We know that we have a very, very low Reynolds number. Then this term dominates the viscosity. And you saw that in lab class 1 when you dropped the spheres through the glycerol. Effectively, the streamlines, because the viscosity was so high, this inertial force was so low, the stream, the particles stuck to the spheres and caused the drag due to skin friction. Whereas if we up the Reynolds number, increase this term, so the flow has more bulk kinetic energy, more inertia, this term then becomes less significant. So that really governs the nature of the flow. So what I've drawn here is an open channel. That's what I deal with. In terms of this module, a lot of the talk deals with pipes. So this is basically the centre of the pipe. So you would inflect this rough boundary that I've drawn here above that. Okay, but I deal with open channel flows, and you'll do this next year in civil parts of your hydraulics. So if we were to model an inviscid flow, no viscosity, we could draw a velocity profile from our roughened seabed or boundary here to the surface, and it would look like this. Okay, just a perfectly straight line. There's no viscosity, so there's no shear forces between the particles. Okay, so there's our vertical velocity distribution. Again, I have to stress again and again and again, inviscid flows are a simplification. And there's certain things we can do whereby we can simplify viscous flow to model it inviscidly, because this is so much more easy to deal with. Okay, the flow comes in and it hits our roughened bed here. So locally, the fluid particles coming in, we'll assume it's an inviscid inflow, just for this example. Particles come in, hit this roughness here, will obviously become very rotational, very chaotic. When we take a mean velocity distribution, okay, so averaged over an amount of time, we get something like that, okay? Technically this would tend to zero at the top of this roughness, but for sake of argument. So at the boundary, and this is massively exaggerated, this profile, we have what's called a non-slip condition. So there's the particles in contact with the boundary do not move. As we get further and further away from this roughness, the instantaneous velocity at any height increases up to a point, and we see this in strong tidal flows in marine environments. When you get towards the water surface, assuming there's no waves, because the Reynolds number is very high, we get almost constant velocity with height. Okay. So now, if we want to look at our velocity profile and work out what it could be, we've got this weird shape. Okay, so this is a turbulent profile. If you wanted a laminar profile, it would be parabolic. Okay, so again, reference back to the lecture notes on this one. It's parabolic laminar flow. This is the velocity profile, and the shear profile, so the shear stress profile will be, sorry, I made a mistake there, it should be half a parabola, because I've cut our domain in half, haven't I? And the shear stress distribution will be linear. So you can demonstrate with a pack of cards. So you put a pack of cards on your hand, and then just shear the top one. You'll see that if you imagine each card is a layer of fluid, each layer is contacting with the layer adjacent to it and transmitting some of that shear force. Okay. If it was an embittered flow, there would be no friction in between any of the cards. Okay. My hand is a non-slip condition, so if I keep pushing and pushing the cards, I'll eventually get to the bottom one here, which doesn't move. Okay, so that's sort of, I could do a magic trick, but I won't. Engineering and physics is magic enough. Right. The issue here is that we want to work out our mass flow rate or the average velocity. And it's very difficult because we've got this awkward velocity profile. Velocity is 0 at the bottom in the real fluid. We've got this boundary layer here, and then at this point here, it finishes, and we have a nice flow here, which is effectively embittered. Okay, we observe this in real life, like I say, in tidal flows. So we could do, if we want to run a split model, we could run the bottom part as a viscous flow and the top part as embittered. That's still not ideal. So what we tend to do is try and assume that this doesn't exist again, which is becomes an embittered flow. It's a simplification. Right. Some key definitions now. So you deal with this when you deal with Bernoulli and things like that. Again, Bernoulli is for an embittered flow. So we just have pressure, kinetic energy, potential. That kinetic term you're working out, the value of U is averaged over the whole flow. It's embittered, so it's the same U all the way. Right, displacement, boundary layer displacement thickness. Displacement thickness is a linear distance. What we're saying is what we want to do is change this shape. We want to maintain this area, but make it into a rectangle instead. So to do that, we have to change the geometry of our channel. What we're going to do is we're going to pull this profile down vertically. So, like so. Because we've done that, we've now got a larger area, so we're going to displace the seabed in this case, or the wall of the pipe upwards until these areas match. Okay, so this distance here is our displacement thickness. Okay. How do you calculate that? Well, you can see it's just a geometric conversion, basically. So if you know the equation of this velocity profile, it's just a case of doing some integration. I doubt if you'd be asked to do that in the exam. Most of the time, this displacement thickness will be given in tables for known geometries and known roughness heights, or relative roughness values. There's also a thing called the equivalent version for the mass flow, or the momentum. Exactly the same thing. We have a mass flow coming in, and then our vertical velocity distribution changes. Remember, momentum is a function of velocity. So this is exactly the same. How far? This is a linear distance we have to move the bed, in this case upwards, so that we can model the whole thing as an embittered flow. These two values are not the same, so these two distances will not be the same for any given flow. That leads to a ratio, which you can find in the notes. And this ratio then, with these two displacement thicknesses, will then effectively it's just a way of describing the flow. So along with Reynolds number, it gives you another indication as to the shape of this velocity profile. So it's for a laminar flow, we've got this parabolic distribution in a pipe, about 2.6. And it's approximately 1.3 turbulent. Okay, so this is sort of a shape factor, if you will. Right, moving on to some conventions. You'll see this this ratio of times, small r divided by large r. So again, if this is a half width of a pipe, this is r. It's some distance away from this point of maximum velocity, so that'll be in the centre of our pipe, or in this case, the surface of an open channel flow. R is the total distance. In this case, it's a radial distance. So we reflect this about the water surface and make it into a pipe. This dimension here is r, from the centre line to the edge. Right, notation for u, velocity. If we use the infinity sign, infinity always refers to a position far upstream or far away from where we are. So you consider it sort of an ambient inflow condition. Now the notation does change slightly in the course notes and in some of the work solutions in the class tests. But generally, small u is the velocity at a specific location. And we tend to use large u and tend to put an overbar on it. That's the average velocity. Okay. So when we're doing integration, you'll see usually u. It can be sometimes capital or lowercase, but that tends to mean the velocity at a radial location when you're doing your integral. Okay. So if this was a pipe, this is the centre, so looking head on. This is our small value r. The radius is large r. What we're going to do is we're going to integrate radial elements of width dr, and each one will have its own velocity, usually small u, but if it's written as large u, it is the same. Obviously the velocity is going to change. If dr is a constant, we have a constant width element, obviously u is going to be maximum here and minimal here. Okay, so that's what we're doing. And we're integrating these radial strips. Okay. Up here, m usually means maximum. So this is effectively some sort of power law. So we could write, for example, again, a bit more, so large u equals u max, so the velocity at any point equals the maximum velocity times some function, so 1 minus little r over big R, and then so basically this is then just a power law. So actually this curve here would be more like this. Okay, 1/7 power law up to the surface, or up to the out from the edge of our pipe wall to the centre line, and then it would go back again to the other wall. Okay, and then obviously this is our, we can work out then the mean velocity. When you did lab class 5, You use the sump, the bench, Q equals UA. Now we had a Venturi section in the pipe, so it was pipe bore, converging section, a narrow throat section, diverging, back out again. You worked out the velocity, and then from that you worked out the kinetic term, R rho u squared, or if we divide through by density, u squared over 2g to give us our velocity head. You worked out the average velocity. We'd measured it with a small velocity probe. We'd measured the velocity in the centre of the pipe. We would have overestimated the average. We'd measured too close to the wall. We'd underestimate it, because let's assume it's a turbulent flow. That was our velocity profile. Okay, it was a viscous flow. What we did, or what you did, was find the average. So again, if we come back to this diagram, the average velocity that we could use for working out mass flow, for example, is going to be somewhere here. Okay, so less than U max. But it accounts for the fact that we've got a lower velocity here in the boundary layer. Okay, so that way you worked out the average bulk velocity. Okay, hopefully that's all sorted. Again, chapter 3, viscid flows, so no friction. Chapter 4, viscous flows. So again, we have this issue with if we have a viscous flow, how viscous is it? Can we make some simplifying assumptions in order to model it as an inviscid flow? Then all of your calculations become a lot easier. You can skip all of this integration to work out the average velocity, things like that. You just apply displacement thickness, which you've probably been given, or given the equation to work it out. And the same with the momentum displacement distance as well. Okay, so we can make some nice assumptions. Basically, if this is a tidal flow, and this boundary layer is small enough, so you get to your maximum velocity down here somewhere, so it's quite small. We can usually say, do you know what, we're engineers, we can add in these functions and model it inviscidly, and then it becomes 10 times more simple to model an inviscid flow than it does for a viscous flow, because we've not got to deal with all of this turbulent motion and losses of energy, or losses of mechanical energy into heat. Okay, good luck with your exams.